another fun story about Greg before he comes on up here is that when he was a kid and had one of his first telescopes, he had seen all these really cool pictures in magazines and his school books and stuff of galaxies. And so he had a good idea of how a galaxy was supposed to look. And when you look the first time through a really little telescope, expecting to see all the detail in a big galaxy, it's not the same. But if you go to Hawaii and help run the Keck telescope, then you get a pretty good view. And he has been an astronomer with a research specialty in galaxies ever since. So let's warmly welcome Dr. Greg Wirth.
Aloha. Thanks for coming tonight. It's a pleasure to be here. This is almost a disaster because I realized a half hour before the talk that I left the power supply for the computer at home. And, until tonight, I didn't think it was a good idea that I let my 16-year-old son get a car with a turbo, but today, very handy. They got here just in the nick of time. So thanks for making that tonight.
Do you have the microphone on?
I believe it. Can you hear me?
Okay.
Yep.
Okay, here we go. Okay.
You can hear me? Good. Tonight I'd like to tell you about a remarkable place, Mauna Kea, the volcano on the center of the island of Hawaii. It's a place that is remarkable because it's home to the greatest collection of telescopes ever assembled. I'd like to tell you about what the astronomers are doing with these telescopes, what technologies they're using that are changing the way they do astronomy, and what the future may hold for this place. Earlier this year, many of us watched in awe as lava spurted from the ground and covered neighborhoods on the big island of Hawaii. Of course, this is not a new phenomenon. This is something that's been going on for millions of years, and it's why the Hawaiian Islands exist. They're all volcanically built as the plate that carries the Pacific islands drifts across a hot spot in the middle of the ocean where lava is forced up and forms this chain of islands. So this is not a new process, the one that's been going on for millions of years. What we know is that the Hawaiian Islands were formed out of this lava, and this is the way that the islands have been growing ever since. The story of Mauna Kea begins a million or so years ago when a volcanic island that had been growing underneath the ocean finally reached the surface of the water and poked its nose up above the Pacific. At that point, this island was already 20,000 feet high, because that's where the bottom of the ocean is at that point. The lava kept flowing, the island kept growing until it stood 2 miles above the ocean's surface. And at that point, the hotspot moved on and started forming other volcanoes in the vicinity. It created the Kolala volcano, it created Mauna Loa, it created Kilauea. And together with the ancient part of the island that's called Kohala, these land masses merged together to form the largest land mass in the Pacific Island chain. Over the eons, ice ages came and went. Glaciers covered the summit of the mountain and carved it up. And the last ice age ended just 13,000 years ago. That's when the last glaciers receded from the top of Mauna Kea. But the island was not done growing. At the top of Mauna Kea, volcanism continued until 4,000 years ago. That's when the most recent of these lava tubes, these cinder cones, was formed. So today, the mountain is said to be dormant, but it's not done erupting. Volcanologists tell us that someday the island will someday re-emerge and erupt again. Humans entered the picture of Hawaii relatively recently. A few thousand years ago, the citizens, the denizens of Taiwan, invented a new technology for transportation. It was the outrigger canoe, a stable craft that would allow them to go great distances across the ocean. And they used this technology to venture out from Asia and go across the Pacific, hopping from island to island and inhabiting new places. Eventually they reached Taiwan, And from there, they made the voyage across the open ocean up to
Like
Hawaii.
stepping up and then stepping back, because sometimes, there.
Good, okay, we've got the AV sorted out. They made the long voyage across the open ocean to reach the most isolated landmass in the world, the Hawaiian Islands. They only arrived there about 1,000 years ago. From the first time they set foot there, they realized that the reason they'd made it that far was because of their knowledge of astronomy. The Polynesians were expert navigators because of their knowledge of the stars. They were able to use the measurements of the sky to determine the latitude and thus make their way across the ocean. So from the very beginning, there was a deep connection between Hawaii and astronomy. The people, the small band of people who settled the island initially founded a civilization that grew and grew over the centuries to thrive and cover all of the Hawaiian Islands. And the people felt that the volcano in the middle of the island, the tallest point that was covered with snow any time of the year, was a holy place. They called it Mauna Kea, the White Mountain. Only the most exalted people were permitted to go to the very top of the mountain. The priests and chiefs would visit there, taking an arduous journey because, of course, they had no horses or other pack animals to carry them. They had to travel by foot, and the journey would have taken them days. And once they reached the summit, they came to a place where the air was incredibly thin and hard to breathe, the temperature was cold, and the weather could change on a dime. So it was not a place to visit lightly. And yet there were reasons besides spirituality that drew them there. Near the summit of the mountain is a ring of rock that is very special. It was formed when hot lava came in contact with glacial ice and cooled very rapidly to form an exceptionally hard basalt that makes very hard rock. This rock can be used to make cutting tools and axes that people can use for carving out canoes to transport themselves across the ocean. So what the Hawaiians would do is they would venture up to the mountaintop and quarry this rock. They would bring it back down and distribute it among their neighbor islands, and even across the Pacific. We find examples of these rocks having been traded. So that was the reason that many people made the journey, the arduous journey up the summit. Looking out from the summit of Mauna Kea, you gaze upon a remarkable island that is varied in its ecological domains. In fact, the island of Hawaii contains 4 of the 5 major domains on the planet Earth. You have the hot tropical beaches. You have the uplands where the rainforest occurs. You have the desert area of the saddle between Mauna Loa and Mauna Kea, and you have the tundra at the summit. In fact, the only major niche, the only major type of climate that is not represented on Hawaii is what we have here in Colorado, the cold continental climate, which is why you won't find apple trees or cherries growing on Hawaii. The arrival of Captain Cook in 1778 was a watershed moment for Hawaii. It brought contact with the Western world. It also brought disease that decimated the population. But there was also opportunity, the chance to learn about the wider world. And over the decades of the 19th century, the monarchs of Hawaii sought to expand their vision for their society. The last king of Hawaii, David Kalakaua, was an enlightened king who sought to travel the world and bring ideas back home for his people. In 1881, he traveled to California by boat, and while there, near San Francisco, he visited the Lick Observatory that was then under construction. The person in charge of the Lick Observatory was Richard Floyd. He'd gone out to Hawaii years before to visit the king and was eager to reciprocate the welcome that he had received. Floyd brought the king up to the summit where the Lick Observatory was just about to install its new telescope, a 12-inch refractor, among the largest in the world at that time, with a lens crafted by Alvin Clark, the master craftsman of lens making of the 19th century. And Floyd made sure that the king of Hawaii was given the privilege of being the first to gaze through this new telescope at this new observatory. Telescopes enter the picture in Hawaii at a later time. For centuries, astronomers built telescopes where the astronomers were, in cities where the colleges were. Around the late 19th century, they realized there were advantages to building telescopes outside of the cities. And so they started building them in places like Lake Geneva, Wisconsin, where the Yerkes Observatory is, where Andrea has done some of her work. This is where the famous Yerkes refractor, the 40-inch telescope, was built in 1897, then the largest in the world. Further west in California, astronomers realized that you could also gain advantages by putting your telescope on a mountaintop to get a clearer view of the skies and get above the haze that was down below. That prompted James Lick to found the Lick Observatory that we mentioned earlier there in the late 1880s on Mount Hamilton, just outside of San Jose. So in the 1950s, the famous Dutch-American astronomer Gerard Kuiper, for whom the Kuiper Belt is named, founded the Lunar and Planetary Laboratory at the University of Arizona. And he sought a place where he could put a telescope to get the clearest possible view of the moon and the planets. This quest took him on a worldwide adventure and eventually led him to Hawaii, where he visited the island of Maui. There, the University of Hawaii had established a solar observatory on the tallest mountain on Maui, Haleakala, also which translates as House of the Sun. So he took his telescope up there and did nighttime observations, and he found that indeed we could get excellent images from the top of Haleakala when the sky was clear, which unfortunately was not very often because the summit was often shrouded in clouds. So undaunted, Kuiper changed his direction. He left the island of Maui and went to explore the Big Island, which had two major volcanic peaks that tower over a mile higher than Haleakala. Mauna Loa has the distinct disadvantage that it is still a very active volcano, erupting about every 6 years on average. Not a good place to put a telescope. But Mauna Kea held balance. It was even a little bit higher than Mauna Loa, and so Kuiper ventured to the summit there. Of course, there was no road at the time. He had to hike up or take a jeep. And when he used his telescope to survey the skies from the summit, he found that indeed the image quality was exceptional up here. He exulted to a friend, Mauna Kea, I believe, is the best place in the world. I repeat, in the world, to view the moon, the planets, and the stars. It is a jewel. And indeed, decades later, we know that he was correct. He found the place that was better than all others. What makes Mauna Kea such a great place to see the stars? Well, first of all, the sheer height of the mountaintop. 13,800 feet is the summit. And I know what you're thinking. We've got 14,000-foot peaks here in Colorado. What makes this so special? Well, the fact is that this is high enough to get you above the clouds, and that's what you need. So the height of Mauna Kea was important. And once you're up there, the clarity of the sky was exceptional. Mauna Kea sits above 2/3 of the Earth's atmosphere. So the air is thinner, and there's less light there's less air for the light to pass through. And although it's necessary for us, air is the enemy of the astronomer. Because light travels from distant stars and galaxies to the Earth. It arrives at the top of the atmosphere perfectly clear. That's why the Hubble telescope gives us such exceptional images. But once it enters the atmosphere, the turbulence in our atmosphere causes the light to blur. And that's what ruins our image quality and makes the stars twinkle. Another reason that Hawaii is a good place to put a telescope is because it's so isolated. The air that travels, the trade winds that blow across the summit of Mauna Kea travel for thousands of miles uninterrupted, so that when they reach the summit of Mauna Kea, the air is very steady. It's not interrupted by convective currents like we get here in Colorado, where the air heats the land and causes turbulence in the atmosphere. So that stable, laminar flow of air contributes to the great image quality. Also, it's a very dry place. This is important if you're an infrared astronomer looking at things in heat illumination, because water vapor in the air sucks up the infrared light, and that's the enemy of the infrared astronomer. Here at the summit of Mauna Kea, you have 97% less water vapor than you do down at the ocean side. so it's a great place to do infrared astronomy. The skies in Hawaii are exceptionally dark as well. It's surrounded by water. The biggest city on the island of Hawaii is Hilo, which is half the size of Longmont. There's only 1/10 the number of people on this big island as there are on neighboring Oahu, where Honolulu sits. And furthermore, because of the importance of astronomy, there are strong local lighting ordinances, such as you have here in Berthoud, that require people to shield their outdoor illumination properly and use astronomy-friendly lighting. So it's not uncommon to walk outside of your front door in Hawaii, look up and be able to see the Milky Way overhead. Finally, and crucially, the mountaintop is accessible. As you can see, the slope of the sides here is rather gentle, as is typical of the shield volcano. That means that it's easy to construct a road to the summit, and they did so in just a few weeks so the trucks could carry the materials to the summit that are required to build a telescope. That sets Mauna Kea apart from the even higher mountain in the Pacific, which is in Indonesia, but which is not something that you're going to be able to climb on. So Kuiper found his jewel. He found a place that better allowed people to observe than any other on the planet. But he lost the contest for funding to build a telescope on this mountain. That distinction went to the University of Hawaii, which had a small astronomy group at the time, but was given money by NASA to build a telescope at this site. They started by building a 24-inch telescope in 1967 and made some initial observations. Then in 1970, they completed the 2.2-meter reflector shown in the back here. That was the first real research telescope on the summit. With the data from this telescope, they were able to establish that indeed, Mauna Kea could produce exceptional astronomical data. As word got out to the astronomical community about how good the conditions were on top of Mauna Kea, astronomers clamored for the opportunity to put other telescopes on there. And Hawaii made a smart deal. They said, you may build on our mountaintop, and in exchange, you will give us some of your telescope time. So every telescope on the mountaintop gives the University of Hawaii somewhere between 10 and 15% of their nights for the Hawaiian astronomers to use. It's been an exceptional deal for the Hawaiian astronomy community. Let's talk about some of these glass giants and other telescopes on the top of Mauna Kea. Looking out upon the various telescopes on the summit, we see that there's a diversity of telescope types. This represents not only the different types of telescopes, but the different strategies that have been used to build telescopes over the last half century. The first telescope to appear after the UH telescope was the CFH, or Canada, France, Hawaii telescope, built in 1979. This is a traditional optical telescope. It has the customary equatorial mount, the massive structure here that allows the telescope to track across the sky by turning only one motor. The mirror is 3.6 meters, which put it among the largest telescopes in the world at the time it was constructed. This is still one of the most productive telescopes on the mountain today. It occupies a place of distinction on the summit, at the highest point where a telescope has been built, giving it some of the best image quality. The telescope specializes today in taking images of wide areas of the sky. That same year, 1979, saw the construction of NASA's Infrared Telescope Facility, or IRTF. The telescope specialized for seeing heat energy from sources in the universe. This telescope is unique in having the capability of changing cameras very fast. In just 15 minutes, the astronomers can change from one camera to another and change the type of observations they want to do. Another interesting thing about this telescope is that it can operate in broad daylight, because the daytime sky in the infrared is almost as dark as the nighttime sky. So you can look at planets and other cometary objects even when the sun's out. That same year, 1979, saw a third telescope appear on Mauna Kea. This one, the UK Infrared Telescope, or UCIRT, was built by the British government. And it still stands today as the largest telescope in the world expressly devoted to infrared observations, with a mirror that's 3.8 meters across. It still is a productive telescope, but that didn't stop the British government from deciding not to fund operations on this telescope any further. A couple of years ago, they sold the telescope to a consortium, and it's now operated by the University of Hawaii, University of Arizona, and Lockheed Martin, which is using the telescope to track orbital debris around the Earth. Mauna Kea turns out not only to be a great place for optical and infrared astronomy, but also to do radio astronomy. This telescope, the Caltech Submillimeter Observatory, consists of a 10-meter dish of aluminum panels that reflects radio waves to a detector so that it can study objects like cold gas in our Milky Way galaxy. The telescope has a distinctive shaped dome, giving it the moniker the Marvel and Martian Telescope. Caltech has decided to decommission this telescope. It is no longer in operation and will shortly be removed and the site returned to its natural state. The largest dish on the summit is the dish of the VLBA, the Very Large Baseline Array Telescope, 25 meters across. This is a radio telescope as well, and it is joined with 10 other telescopes that cover a quarter of the planet to act like one giant telescope. There are 10 dishes here, all controlled from a central location in New Mexico, that point to the same object at the same time and transmit their data back to headquarters where it can be combined to provide the resolution of a telescope that is 5,000 miles across. So this telescope has exceptional ability to see detail in radio waves. The most recent addition to the Summit Telescope Menagerie is the submillimeter array, built by the Smithsonian Institution of the Government of Taiwan. This telescope consists of 8 dishes that operate together to form radio images of the sky. When they're in, and the telescopes can be moved. The individual dishes can be moved to change the properties of the telescope. When you put the dishes close together, they operate like a wide-angle lens, giving a view of a wider area of the sky. But when you put them further apart, they act like a telephoto lens, giving you a magnified image of a smaller region of the sky. Like the other radio dishes on the summit, this telescope is specialized for looking at cold gas, like the neutral hydrogen in galaxies or the clouds of gas in our own galaxy that are forming new stars. After 10 years without a new optical telescope being built, the 1990s saw not 1 or 2, but 4 massive new telescopes appear on Mauna Kea. One of them is the Gemini telescope. This telescope features an 8-meter primary mirror that is much larger than the previous generation of telescopes. It's called Gemini because it has this twin that lives down in Chile. And these telescopes are so expensive that they were built by a consortium that included the governments of not only the United States, but also Canada, Argentina, Chile, Australia, and South Korea. Those are the members of the consortium. The ability to have one telescope in the north and one in the south means that the Gemini Observatory can view the whole sky over the course of the year, both the northern and southern celestial sites. That 8-meter mirror that we see here is quite a technical achievement. It used to be that when you made a telescope mirror, you started with a big blank of glass that was like a hockey puck, flat on top, and you had to carve out a curve at the top of it to form the shape that would reflect the light back to a focus. And it literally took years to make a telescope mirror that was 5 meters in diameter. With the new generation of telescopes, the mirror is cast in almost the right shape through advanced technology, so that it takes only a year or so to create this beautiful surface. Another thing to note is that the telescope is rather thin on the edge. The so-called meniscus-style mirror means that if you were to tilt this the telescope down toward the horizon and thus move the mirror up out of the nominal position, it would sag under its own weight and deform. So in order for this telescope to work, you have to have an active mirror support system that adjusts the pressure on the back of the mirror so that it maintains its shape. The Gemini telescope also has a simpler mount than the old style of telescopes like the Canada-France telescope. It has the ability to turn in one axis, we call that the azimuth direction, and it has another axis of rotation here, which we call the altitude direction. So this alt-azimuth style telescope requires computer control to move the telescope in 2 axes and track things across the sky. That's why they didn't build telescopes this way in the old days. But this allows the telescope to be built in a more compact fashion. The Gemini telescope has made great contributions to the study of exoplanets by doing direct imaging of some planets around distant stars. That same year that Gemini came online, in 1999. It was joined by another similar telescope with an 8-meter optical mirror. This is the Subaru telescope, built by the government of Japan, not in Japan or Asia, but they put it in Hawaii because of the quality of the characteristics of Mauna Kea. The telescope is distinguished by this distinctive dome, which has a wide slit that can open up and allows the air to pass smoothly over the telescope structure to preserve the great seeing that's available on Mauna Kea. The telescope is named for the constellation that we call the Pleiades, but that in Japanese is Subaru, shown here on the right or the left shoulder of the constellation Taurus. This telescope specializes in wide-angle images of the sky. The last two of the telescopes I'll talk about on Mauna Kea tonight are the two giants of the Keck Observatory. The Keck 1 telescope shown here came online in 1993. It was joined by the Keck 2 telescope in 1996. And together these two are the queens of the summit, each with mirrors that are 10 meters across. These telescopes were not built by a government. They were built by two universities, California Institute of Technology and the University of California, based on a generous bequest from an oil baron, William Keck, who gave money to fund these telescopes. When these two telescopes came online, they were incredibly more powerful than anything that had come before. Up to that time, the gold standard was the 200-inch telescope on Mount Palomar. These telescopes each have 4 times the light gathering power and are at a much better sight. So astronomers who had access to the Keck telescopes had a huge leg up on the competition. They could do in a single night the types of studies that would take their competitors weeks or months to do. So it invented a new term that was popular in the 1990s. If somebody beat you at something, you've been kecked. The advances that led to the ability to make this 10-meter mirror were primarily technological. In particular, the Keck mirrors consist not of a single piece of glass, but of 36 individual hexagons that are put together to act like a single mirror. There was great debate in the 1970s about whether this segmented mirror technology could work. It turned out that one of the interesting technological challenges was how to polish these mirrors. Here are some of the segments shown in the mirror. Each of these is 1.8 meters across. And on the left side here, you can see what one of the segments looks like without its aluminum coating, showing the support structure that's behind it. To make these mirrors was a challenge because together they all have to form a perfect parabola shape, meaning each one is a segment of a parabola. And it's an off-axis parabola, which is a difficult shape to grind. But grinding spheres is very easy. So what the Keck inventors did was they took each mirror blank and they put it in a vise to deform it. They stressed it to a particular shape. Then they polished it to a spherical shape, took it out of the vise, and allowed the glass to relax into the shape of a parabola. Then they sliced off the edges of the round blank to form these hexagon shapes and put them together to form a mirror. It was a brilliant idea. This is what a segment looks like. You see it here from the side, and the backside of the segment is reflected in these other segments. So this is the segment that's pulled out of the stack. It's relatively thin, only 4 inches thick, and it's got this big support structure here. Doing a segmented mirror requires exceptional computer control. The positions of these segments have to be controlled to a tolerance of only 4 nanometers. That's 1/25,000th the width of a human hair. And the adjustment needs to be updated twice each second so that each of these segments stays in line with its neighbors, and together they form a perfect mirror shape. The Keck telescope technology was a brilliant idea and allowed these two telescopes to be the most scientifically productive ones on the planet Earth. And the segmented mirror technology can be scaled up to form even bigger telescopes, as we'll talk about later. The telescopes are amazing tools, but they are just machines. They do not make the discoveries. In fact, they're just the tip of the iceberg in what is required to turn astronomical data into astronomical discoveries. How does the astronomer go from idea to discovery? It begins with an astronomer asking a question, an idea about the universe, something they want to understand better. They take that idea and they talk about it with their colleagues, and they decide what type of data they're going to need to address that question and what observatory is best suited to deliver those data. They'll then get together and write an observing proposal, a document that says, this is what we'd like to do, these are the data we need, and this is why it's important. And they send that into the observatory. Any good observatory gets far more requests for telescope time than it could possibly fulfill. So all of those requests get collated and sent to a committee of astronomers, the Telescope Allocation Committee, whose job it is to sift through all these requests and decide which ones have the greatest scientific merit. They will then award time to the ones that receive the highest scores. Lucky astronomers may get 20 nights on the Keck telescope to do world-class research, but many people will feel lucky to get a couple of nights, or a single night, or a half night to do their work. Once the astronomers know that they're getting time, they have the opportunity to prepare for their run by deciding exactly which targets they're going to look at for how long. And they prepare star charts so that when they get to the telescope, they'll be able to find what they're looking for. In the days leading up to their run, they will consult the website of the Mauna Kea Weather Center, a weather project specifically devoted to predicting what's going to happen on Mauna Kea. Not only what will the temperature be and what will the wind be doing, but will it be humid so that the infrared is going to be effective? Will the seeing be good? And will there be fog? The astronomers know that if the weather turns bad in their summit night, they don't get a makeup date. They have to go back to the drawing board and reapply for time the following semester. The day before their observing run, the astronomers get on a jet plane and fly to Hawaii. Once they get there, they rent a car and they drive halfway up the summit of Mauna Kea to a place known as Hale Pohaku, the astronomer's residence that lies at the 9,000-foot level. There they're in sort of a hotel where they can rub shoulders with astronomers that are using other telescopes while their needs are catered for by a small army of people who cook meals for them, change the bed sheets, run a road grader up the gravel road to keep it smooth, or even plow the top of the road if it's snowy in the wintertime. On the day of the observing run, the day crew at the summit will reconfigure the telescope for the astronomers. They'll make sure that the right instrument is loaded, that that instrument has the appropriate filters, that the cryogens to cool the instrument are loaded, and that everything is checked out and ready for the astronomers to use. The astronomers will have their dinner and then endure a bone-jarring trip up the gravel road to the summit. There'll be a sigh of relief when they reach that paved part that comes just before the summit. When they reach the summit, they won't be alone. People drive up that summit to see the sunset from the highest point in the Pacific Basin. As they watch the sun slip beneath the horizon, you can hear the whoops and hollers. Then the sun goes down and the temperature drops to right around freezing. The people who were up there before will retreat to a lower elevation. And it's an interesting point to note that up at the summit, the oxygen level is so low that it affects your night vision. It turns out that you can actually see more stars from halfway up the mountain than you do on the summit. So the sun goes down, the telescope operator opens the dome so that the telescope can reach the outdoor temperature. If the telescope mirror is warmer than the outside air, that's bad, because this massive mirror will heat the air above it, set up convective currents, and create little turbulence over the mirror that will ruin the perfect seeing that Mauna Kea provides. If the mirror is too cold, even though it's dry up there, it's possible the moisture could condense onto it. So the day crew has been monitoring the predictions about tonight's temperature, and they've set the thermostat inside the dome to what they think the outdoor temperature will be at sunset. In fact, one of the greatest expenses for operating these observatories is the air conditioning bill. It can be tens of thousands of dollars each month in electricity to keep those air conditioners operating. The sun goes down, the dome opens up, the telescope operator slews to the vicinity of the first target and looks for a star in the twilight that they can focus on. They find it and focus the telescope, and if we're observing the infrared, we can start working right away because the sky is already as dark as it's going to get. If we're looking in the visible light, we need to wait a little while for astronomical twilight, when the sun has gone far enough below the horizon that the sky is truly dark enough for us to begin observing. The telescope operator will sit at a bank of computers all night long, often working 14-hour nights for several consecutive days. There they will monitor the condition of the telescope, the dome, the instruments, and of course the weather. Another member of the team is the support astronomer. That's a team that I was a member of. Here's my colleague, Mark Cassis. The support astronomer is there to help the astronomer get started in the afternoon, teach them how to operate the instrument and take their data, and be present throughout the evening until the astronomer is going smoothly. For some people that takes an hour, for others it takes quite a while. After he leaves, the astronomer will have the cell phone by the bedside all night. He'll be on call in case something goes wrong. He'll have to leap out of bed to the computer and try to fix something if the astronomer is having trouble. The observers don't operate from the dome, of course. They sit in a nice heated control room, gulping cup after cup of coffee to stave off the exhaustion that comes with trying to stay up all night after you've taken a jet flight and changed several time zones. They're not going to have probably any aha moment during the night. That will come later. Instead, what they have is several minutes of frantic activity each time they go to a new target to get the telescope set up and the observation to begin. And then an hour of boredom while they wait for the instrument to gather their photons. As the night goes on, they'll keep a wary eye out for clouds. If any fog gets on the telescope mirror, it could ruin the precious aluminum coating that reflects the photons back into the instrument. So weather cameras are set up on each of these telescopes that look out in all directions, and that the observing assistant or telescope operator can monitor all night for signs of fog. If the fog rolls in, the dome gets closed and won't reopen until the fog is gone. As the night goes on, the stars whirl by overhead. The astronomers try, whenever possible, to observe the targets when they reach the apex of their arc, because that's when they're looking through the minimum amount of atmosphere. But usually what ends up happening is the astronomers will chase objects far into the west, trying to get as much time on each object as possible. Another member of the team is the engineer that's on call. If something goes wrong with the telescope or the dome during the night, there'll be a phone call to an engineer who will be awakened perhaps some ungodly hour of the morning. If he's lucky, he'll be able to fix the problem from a computer. If he's unlucky, he may be asked to get in a car and drive 2 hours to the summit to try to salvage what's left of the observing night. With the value of these telescopes, the time is worth about $3 per second on sky. So it's worth it to try and salvage even an hour of time for the astronomers. Eventually, the night ends and the sun begins to rise. If the astronomers dash outside at sunrise to look to the west and see what looks like a mountain in the sky, but of course it's not a mountain, it is just the shadow of Mauna Kea projected off into infinity as the sun is rising. The telescope operator parks the telescope, closes the dome, and submits the results of the night's observing in the form of a report, the night log, that will go out to everybody at the observatory who's a technical person. For a while, the telescope will be vacant before the day crew arrives. When the day crew makes it up, they'll make decisions about what to do that day. If there were problems during the night, their first priority is going to be to try to fix those issues so that they don't reoccur tonight. If there are problems, they'll try to get on with the business of keeping the observatory running. They may get up in a man lift and use carbon dioxide snow to blow debris off of the primary mirror and keep it clean. The people responsible for maintaining the coatings may have the opportunity to strip the coatings off of an old segment and put on a fresh coat of aluminum. And other technicians and engineers will try to maintain the instruments and telescope to keep them working well or provide needed upgrades. And so it continues night after night, 365 nights a year. Telescope time is so valuable that they won't even take time off for Christmas as the stars whirl overhead. As I said, there won't be an aha moment during the night for the astronomers. That will come later. After the observing run is done, the astronomer may have an afternoon to enjoy the delights of Hawaii before getting back on a plane and heading for the mainland. And on the way, they get a chance to look at the data before they get back involved in the day-to-day grind of teaching classes, advising students, reading the journals. Eventually, they will get a chance to look at their data and perhaps make a discovery. And when they do, they may write it up in the form of an article for a scientific journal perhaps months or even years later. When they do, other astronomers will read about it. And this is really the end product of what the astronomers are doing. This is how we measure the productivity of a telescope, based on how many publications are generated in the scientific literature each year. Of course, not every discovery is equally noteworthy. You can actually measure the impact of a paper based on how many other astronomers refer back to that paper when they write their own. So you can do an interesting statistical analysis of how productive telescopes are based on these publications. My colleague Dennis Crabtree in Canada has done this. He found that you can evaluate telescope productivity in two ways. You can talk about the quality of the average discovery from each telescope, and you can talk about the total quantity of discoveries that come out of each telescope. So on this graph, you want to be up here in the top corner if you're doing really well. And here I put squares around all of the telescopes that are on Mauna Kea. You can see that they represent a wide swath of the very most productive telescopes on Earth. So the Mauna Kea telescopes are really world leaders when it comes to doing science. Of course, the scientific literature is not the only way that we measure the impact of astronomy. It's also the popular literature that's important. That's why you're here tonight, because you've learned about astronomy and you think it's exciting. So it's exciting for us when science gets written up on the pages of magazines or appears on the news. In fact, this one article on the left is interesting to me because I played a role in the cover story, having been there the night that the writer from Time magazine was there doing the story. In fact, I have a little excerpt I'd like to share with you that he wrote about his experience there that night. The article begins painting a picture of what it was like in the control room. Richard Ellis, famous astronomer from Caltech, paces impatiently back and forth across a small room lined with computer terminals, trying to contain his mounting frustration. The British-born astronomer now at Caltech has been granted a single precious night to use one of the two twin Keck telescopes, among the most powerful in the world. But things are not going right. It goes on to explain that the Keck telescopes were brought to their knees by the fact that somebody mistyped one character when entering the name of the observers that night. It was not a banner evening for us. Turns out my mother gets Time magazine, and when that story came out months later, she read it and talked to me on the phone and said, "So just who was it that night that was on duty when that stuff?" So be glad that whatever you do, your worst day at the office is not likely to become this conversation. We talked about the telescopes. I'd like to give you a brief description of what some of the interesting discoveries these telescopes are making. Exoplanets are one of the most fascinating areas. We're discovering planets around other stars at a dizzying pace. And the telescopes on Mauna Kea have been at the forefront of these discoveries in two ways. First, we're using spectroscopy to measure the Doppler shift in stars and their motions that's induced when planets orbit. We're also now to the point where we can take direct images of certain exoplanets and see the planets around other stars. The skies among Mauna Kea, being so dark, are a wonderful place to gaze deeply into the sky. So you see not only exoplanets that are nearby, but you can see the distant galaxies. Here in this image from the Canada-France-Hawaii telescope, we see lots of bright blue things. Those are stars within our own galaxy. But nearly everything else here is a separate galaxy in its own right, just like our Milky Way galaxy, but far, far away. Some of them may be things that were baby galaxies at the time the light that we're seeing now left them billions of years ago. Another interesting discovery relates to supernovae. A given galaxy will have a supernova go off maybe once every 100 years. It turns out that if you look at lots of galaxies, though, you can see lots of supernovas. And the Subaru telescope looked at one particular area of the sky, probably something that you could cover with the edge of your fingernail, many times, and saw not just a few, but hundreds of supernova events. And it turns out that from these supernova events, you can measure the distances to galaxies, and you can infer how the universe is expanding. We've known for 100 years that the universe is expanding, but 20 years ago, astronomers thought that that expansion must be slowing down due to the gravity of everything that's in the universe. What the astronomers found when they looked at this was actually the expansion is speeding up over time. The universe is accelerating due to a force we don't really understand yet, but we refer to as dark energy. It acts like an anti-gravity that causes the galaxies to fly away from each other. And for making this discovery, which the Mauna Kea telescopes contributed to, these 3 astronomers earned the Nobel Prize in Physics, the highest honor the field can bestow, in 2011. New technologies are changing our life, and astronomy is no different. One of the things that makes it challenging to do astronomy on Mauna Kea is the thinness of the air out there. It's a terrible place to try to operate. You can't think straight in the thin air out there. So for years, we've been trying to get astronomers to be able to operate telescopes remotely. The Keck telescopes were leaders in this. 20 years ago, they initiated remote observing from the headquarters building in Waimea at the comfortable elevation of 2,500 feet. Here, the high-speed data link to the summit allowed the astronomers to use the telescopes just like they would at the summit, but with the added bonus of being able to walk next door to a restaurant or go out to Starbucks for late-night coffee. Of course, now that we have fast internet all over the world, you can not only do this from the Hawaiian Islands, but from anywhere. So the Keck telescopes have established remote observing stations across the United States and even as far as this one in Australia. So now the astronomer, instead of having to jet across the Pacific to do a night of observing at Keck, can simply walk down the hall to an office. Less romantic perhaps, but far more convenient. Some telescopes are even going further and have taken the opportunity to take all of their nighttime staff off the summit. For example, the staff of Canada, France, Hawaii now operate their telescope from Waimea because they've upgraded all their systems to be reliable enough that you don't need somebody up there to hit a button. And now astronomers are to the point where they may not even be involved in taking the data. In today's world, there's something called Q-scheduled observing, where the astronomer simply submits a set of instructions to the observatory. And people at the observatory have the telescope open during the night and make constant evaluations of what the current conditions are. Is this a good time to be doing infrared astronomy because the water vapor went down? Or is this a better time to be doing something else? And they'll make those minute-by-minute decisions and switch from one program to another. And then they'll email or communicate the data files to the astronomer at a later time. The most exceptional new technology comes from the instrument side. It's something called adaptive optics. This is how astronomers are taking the twinkle out of starlight. The adaptive optics system is a fantastic optical creation. It's a device that sits between the telescope that collects the light and the instrument that analyzes the data. Perhaps about the size of a phone booth. Light comes in from the telescope and goes through the optics of this amazing mechanism. Some of the light will hit a beam splitter here, where the red light gets redirected to the camera. Other light will be directed to an analyzer. Without the adaptive optics system, the image dances around due to the turbulence that's in the Earth's atmosphere, and the image is blurred. But this analyzer is the key. You can think of the light as it comes in as being wave fronts, sort of like a potato chip when it's gone through the turbulent atmosphere. It has distortion that causes the blur. But this analyzer will take a look at those distortions, figure out what they are, and it sends signals to this amazing thing called a deformable mirror, which can change its shape 1,000 times each second. When those deformed wave fronts come in, they put the anti-distortion into that mirror to flatten out the wave fronts and turn what was once blurry light into light that is as it was at the top of the atmosphere. So the camera now sees images that are as sharp as what you would see with the Hubble Space Telescope. It's not magic, it's technology. There's one problem with this, which is that in order for the adaptive optics system to be able to measure what the distortion is, you need a fairly bright star to be near the target you're looking at. It turns out only about 10% of the sky meets that criterion, which means there's a 90% chance that the interesting target you want to look at won't work. Wouldn't it be nice if there were a way to take a bright star and put it wherever you were looking so that you could make those measurements? And it turns out there is. Astronomers are using lasers. This laser pointer in my hand passes through the air until it reaches the wall where it's reflected back to me. Similarly, the astronomers have attached lasers to the sides of the telescope so that wherever the telescope points, a laser beam goes into the atmosphere up 60 miles to where there is a layer of sodium atoms. Those atoms are deposited there by meteoroids that hit the Earth's atmosphere and burn up and leave some sodium up there. So this laser has an orange color because it's tuned to the wavelength of the sodium atom. That sodium wavelength light, it passes right through the air, but when it gets to the top of the atmosphere and reaches the sodium atoms, it's just like my laser pointer hitting a wall. There's a dot up in the sky. And that is how they can use the adaptive optics system wherever they want to look. Many of the telescopes on Mauna Kea now have these adaptive optics systems, and they allow you to do fantastic work. On summer nights when the galactic center is overhead, you can see 4 different telescopes pointing their lasers at the galactic center. Why do they want to look at this particular place? Because there's something fascinating going on there. Without the adaptive optics system, you look at the middle of our galaxy, you just see a bunch of blurry things. But turn on the adaptive optics system and make the images sharp, and you can make out individual stars that are in the middle of our galaxy. And when you watch those stars over time, what happens is you can see them move. Astronomers have monitored these stars for 20 years and mapped out the orbits that these stars are making. It turns out that all of them seem to be going around this one location right here that's marked with a star. But there's nothing apparently at that location, nothing we can see. And yet from basic Newtonian physics, we can tell that the mass that is there is enormous, 4 million times the mass of our own sun. And yet it must be small because stars can pass quite close to it and not be disrupted. So what could be very massive, very small, and invisible? Black hole. We believe there's a supermassive black hole at the center of our galaxy, and in fact at the center of pretty much every galaxy. So this is just one of the amazing things that we're doing now with this amazing technology. So, the Hubble Space Telescope and the soon-to-be-launched James Webb Space Telescope are phenomenal instruments for doing astronomy in orbit. But there's only 2 of them, and there are many astronomers that would like to use them. They can't do all of the science. That means that the Mauna Kea telescopes will be contributors to astronomy for decades to come. That is, if they continue to exist. For there is a debate that's been raging in Hawaii for 20 years about the proper use of the summit of Mauna Kea. On one side are the astronomers who want to continue using these incredible machines of discovery and perhaps build even more at this best of all sites to do astronomy. On the other side are opponents of new development who want to not have any new telescopes on what they consider a holy site, and some of whom would like the telescopes to be removed and the site returned to its natural state. What is certain is that if there's any new development on the summit, it will be very limited. The University of Hawaii administers the summit on behalf of the state of Hawaii and has come out with a new master plan that they've developed in consultation with many stakeholders. The new plan sets forth new ways to protect the delicate ecosystem of the summit, which includes Lake Waiau, the only alpine lake in the entire Pacific, a place where for centuries Hawaiian families have brought the umbilical cords of their newborn children to leave in the lake as an offering. There are also many cultural sites on the mountaintop that will be protected through the new plan. In terms of astronomy, the plan calls for the construction of just one new telescope, the so-called 30-meter telescope that Caltech and the University of California would like to build, which offers 10 times the light-gathering power of the existing Keck telescopes. This would be an enormous advance that would keep Mauna Kea at the forefront of astronomy for decades to come. The battle over what to do with the top of Mauna Kea has led to contentious hearings and court cases that have delayed the construction of the TMT project. This has led the TMT backers to consider going to a backup plan and building the telescope on another place. They know that if they wait too long, other telescopes that have already broken ground in Chile will beat them to the punch and they will be left in the dust. So they face a difficult decision about how long to stick with the idea of building telescopes on Mauna Kea. If the TMT goes to another place, it will be a turning point for Hawaiian astronomy, and Hawaii may recede from its prominent place on the world stage. With the future being uncertain, astronomers will continue to flock to use these telescopes in the pristine environment of Mauna Kea. We study the stars to learn about our own origins. We now know that we are made of material that is 10% left over from the Big Bang, 17% material recycled from other stars, and 73% of what we're made of is the ejecta of supernova explosions in the distant past. These atoms come together for a time to form sentient beings who can ask questions. Eventually they will return to the Earth, and someday eventually to the cosmos. We come from the universe, and now we are the way that the universe studies itself. And Mauna Kea and the telescopes upon its top have been our best tool for doing so. Mahalo. Thank you very much. Appreciate you all coming out, especially on a baseball night. There's no World Series for this. Are there any questions?
So, with the 30-meter telescope, I know that the agreement is to remove telescopes as well, too, to get it built. Which ones are being removed?
The ones that would be, so the question is, will they be removing telescopes from the summit of Mauna Kea, and if so, which ones? Well, it will be the ones that are presumably deemed least productive. As I said, the Caltech Submillimeter Observatory is being decommissioned. I think the, gosh, I didn't even show the JCMT. I left one telescope out, but there's another radio telescope that I didn't mention tonight, and that will also be removed. Aside from removing old telescopes, another option is to repurpose existing domes. For example, the dome for the Canada, France, Hawaii telescope is nearly as big as the Keck domes, even though it holds a very small telescope because it's an outdated technology. So one of the ideas has been to remove the existing telescope from the dome of the Canada, France, Hawaii telescope and replace it with a newer, larger mirror that could do much better science. Other questions?
They do it by the hour, charge by the hour, by the month?
Do they charge by the hour or month? Well, telescope time is awarded in different ways on different telescopes. On classically scheduled telescopes like Keck, typically you are assigned a night or half a night or so on that is explicitly for you. On other telescopes, for example, the Q-scheduled telescopes like Gemini, you may be given up to 30 hours of telescope time, and you may receive that time in little chunks over a period of time. And depending on how highly ranked your proposal is, you may get all of your time or some fraction of the time, depending on how much of the observing program you're able to get through.
Like about 20 bucks?
20 bucks a time? No, as I said, typically 20 bucks a time on big telescopes would buy you about 10 seconds. So that wouldn't be too cost effective. Yes?
Exactly who all has access to these telescopes? And then along with the information, is that shared with our government? Or where does all this information go that's collected?
Yeah, good question. So who can get time on these telescopes and where do the data go? Different telescopes have different policies. The Keck telescope being a privately funded or run by two universities, the time is allocated to the various universities that are part of the consortium. Other telescopes, for example, the Gemini telescope, which is funded by your tax dollars, time on that telescope is available to any researcher throughout the world. Anyone can apply for time on those telescopes. And actually, even on the Keck telescope, which is nominally private, NASA is now one of the funding partners of the Keck telescope, and anyone throughout the world can apply for time through NASA. The second part of your question, where do the data go? The data from the telescopes is archived, and stored, in the case of the Keck telescope, there's a Keck telescope archive that's run through the Jet Propulsion Laboratory in California, so that anyone, you with a computer, can go home tonight and download data taken at the Keck Observatory. There is a proprietary period of 1 year for most observations. That's so that the astronomer who proposed the program has a period of time when they have exclusive access to that data to make use of it, so they don't get scooped by their competitors. But once the expiration period expires, the data are freely available for download. And most, if not all, of the telescopes are now going to this model in recognition that the money comes from the public, so the data need to be public as well.
I got one question with little 3 caveats. So if you're observing on a small beam area, how do they get around the existing satellites, the space jump? Do they have to somehow miss airliners? And then have they ever seen a UFO?
Okay, so interesting questions there. The first one, how do you see around the satellites and space jump? It turns out that you accept that throughout some of your observations, satellites are going to pass through your exposure. And so when an astronomer takes an image, they usually don't take just a single image of a target in the sky, they'll take several images so that if a satellite happens to pass through one of the images, they can throw that one out and keep only the good ones. Happens all the time, and it's usually not a problem. The second question, I'm sorry, was...
So like if airliners also, you know, one of
Airplanes.
Yes, contrails.
Airplanes can also come through your exposure. Mauna Kea happens to be a place where you don't get a lot of air traffic. There's like one flight that goes between Australia and Los Angeles and passes right over the island each night. The chances it ends up in your exposure are relatively low, but it does happen. And again, you may have to throw out exposure if an airplane passes through it. But not much air traffic in Mauna Kea to worry about. And have I ever seen a UFO? No. Do I know anybody who's seen one with the telescopes? Unfortunately not. That would be pretty cool. But I'm not aware of anything. Okay. Hey, feel free to come up and ask me questions later. I know we've got probably a lot of kids here who are interested.